what is humanity's greatest fear? Is it darkness? Is it death? Or is it loneliness? Distances. One of the universe's most ruthless rules. Between us and our loved ones, sometimes there are oceans, and sometimes just a wall. We want to be there, but we're here. The laws of physics are rigid. The speed of light cannot be surpassed. You cannot be in two places at once. Science fiction films have their essential elements.
Scotty, beam us up fast.
And one of them is teleportation. You just press a button, escape Istanbul traffic in seconds, and appear in New York. For those of us living in Istanbul, that sounds wonderful, doesn't it? Anyway, now I have some good news and some bad news for you. The bad news is this. According to the laws of physics, for our bodies to be teleported, they must first be broken down into their atoms and cease to exist. In other words, we technically have to die. And now for the good news. Are you ready? Scientists have successfully achieved teleportation. But they didn't do it with a person, they did it with light. Last month, in November of 2025, news from the University of Stuttgart showed that one of the biggest obstacles to this technology has been overcome. This development is so significant that we might be witnessing the birth of the quantum internet right now. And don't think I'm exaggerating. In 1969, when two computers sent a message to each other for the first time in a project called ARPANET, the foundation of today's internet was laid. Only a few bytes passed through that cable that day, but it changed the world. And today, we are on the verge of a development that could fundamentally change our perception of time and space. So where did this story begin? Let me take you on a journey through time. The year is 1935. Albert Einstein, considered one of the world's greatest minds, could never accept something about the quantum world. In fact, it kept him up at night. In quantum mechanics, some particles become so connected that even if they're at opposite ends of the universe, they continue to act as a single entity. In physics, this is called quantum entanglement. Those who follow this channel are probably quite familiar with this concept. Not in great detail, but I feel I have to mention it, even if it's just briefly. You can think of quantum entanglement as the universe's most incomprehensible bond. Once two particles touch, that is, become entangled, they are no longer two separate things. They share a common destiny. One of the best examples for this is the glove analogy. Let's say you have a pair of gloves. You put one in a box and leave it on Earth. You put the other in another box and send it to Mars. The moment an astronaut on Mars opens the box and sees it's the right-hand glove, they instantly know what's in the box on Earth, the left-hand glove. Now, this might seem very normal to you, right? You might say, well, if one of the gloves is right, the other must be left. But in the quantum world, the situation is much more interesting. Until those boxes are opened, it's not clear whether the gloves are right or left, my friends. They're both right and left at the same time. In other words, they're in a state of superposition. But the moment one is opened, the other, even if it's millions of kilometers away, instantly determines its fate. And this is what Einstein couldn't believe. He said, this is impossible. In the universe, no information can travel faster than light. One particle can't instantly sense that the others come out of the box. This isn't physics or anything. This is sorcery. Of course, he didn't say it exactly like that, but he used an expression like this: spooky action at a distance. However, experiments conducted in the following years revealed that this spookiness was real. It's as if there's a secret tunnel in the universe's operating system that doesn't care about distance. Scientists have now started asking this question. Since these particles are connected by an invisible string, can we use this string to teleport information from one place to another? For years, this question remained just a mathematical equation on physicists' blackboards. But in 1993, a significant development occurred. The physicist Charles Bennett and his team, in a paper they published, proved that this was theoretically possible. So the answer to the question became clear. We can theoretically teleport information from one place to another. But don't start packing your bags just yet. Because in the quantum world, this process is more like communication than transportation. Meaning, it doesn't mean physically teleporting from one place to another. We can compare it to a fax machine. For example, when you send a fax from Istanbul to New York, the paper itself doesn't cross the ocean, does it? The information on the paper is scanned, then converted into a signal. And the machine in New York uses another piece of paper to recreate that message there. Well, quantum teleportation is exactly that. It's like a universal fax machine. So if you're going to teleport an atom, you can't just pick it up and throw it. You have to read its quantum state, its identity information, and send it to the other side through that invisible entangled line. The other side can then use the raw material it has to build an identical atom according to the recipe it receives. But there's a very fundamental principle here, the no cloning theorem. There can't be two identical copies of an atom's quantum identity in the universe at the same time. So the instant I send the information of the atom in Istanbul to New York, the original atom in my hand has to disintegrate and disappear. So this isn't like the copy-paste function on a computer. It's more like cut and paste. So did this all remain theoretical? No. We've actually been doing this thing that sounds like science fiction for years. In 1997, in Austria, Anton Zeilinger and his team succeeded in teleporting a photon, a particle of light, for the first time in a laboratory setting. Then, in 2004, the rules of the game changed. Two rival teams, one working in America and the other in Austria, achieved a historic success at almost the same time. For the first time, they teleported the quantum state of an atom to another atom. So the quantum state was teleported not just in light, but in material systems as well. We got closer to the Star Trek dream than ever before. In 2017, China took this craziness to space. Quantum information was sent to the Messias satellite, about 1,200 kilometers above the Earth. Now, all of these were very important developments. But there was still an obstacle, an insurmountable wall. All of these systems operated in a closed loop. They could only communicate with other systems that spoke the same language. Because in the quantum world, for two particles to become entangled, they have to be indistinguishable from one another. In other words, they must be absolutely identical. If one atom or light source emits a photon at a slightly higher frequency, that is, a different color, the other system perceives it as foreign and can't communicate. Think of it this way. Let's say we have the two most expensive and powerful quantum computers in the world. One of them speaks Turkish and the other speaks Japanese. In that case, does it matter how powerful they are? They can't even say hello to each other. The language barrier between them prevents all communication. Well, the news from Stuttgart broke down that barrier. Tim Strobel and his team from the University of Stuttgart in Germany crossed this supposedly impossible threshold. For the first time, teleportation was achieved between two completely different quantum dots. So, how did they do it? Did they change the system? No. They took a much smarter approach. They said if we can't change the system, we'll change the language. They used a method called frequency conversion. They took the photon from source A, and without disturbing its delicate quantum structure, they simply changed its color, its frequency, converting it into the language the other system could understand, its wavelength. And a high degree of compatibility was achieved. These two systems, one speaking Turkish and the other Japanese, thanks to the universal translator between them, heard and understood each other for the first time and became entangled. So, how do we know how reliable this transfer is? In the scientific world, there's a fidelity test. If your process is a classical copy, your accuracy rate according to the laws of physics can never exceed 67%, or 2/3. It's a ceiling set by physics. But the Stuttgart team broke through that ceiling, exceeding 72%. Meaning this wasn't a coincidence, it was a proven, genuine quantum achievement. This development is revolutionary, because now for teleportation to work, the devices and laboratories around the world no longer need to be uniform. For example, in the future, an IBM quantum computer could communicate with a Google processor, or a Chinese satellite in space could talk to a European ground station with no communication issues. In other words, that lab in Stuttgart didn't just conduct a successful physics experiment. The foundation for a global quantum internet was laid. Okay, so all this happens in the lab, but how does this data get to our homes? Are we going to dig up the streets and lay quantum pipes? No, of course not. The answer is hidden in the thin glass wires under the ground that let you watch this video. I'm talking about fiber optic cables. Until recently, scientists thought quantum teleportation could only be done in what's called dark fiber, isolated special cables with no data traffic. Because quantum signals are so sensitive, so fragile, that the noise from normal internet traffic could destroy them in an instant. We can compare it to a highway. Imagine the Netflix movies and YouTube videos we watch as massive trucks speeding down that highway. And quantum data? It's like a delicate butterfly trying to fly between those trucks without getting crushed. Well, scientists have now managed to fly that butterfly between those giant trucks without it getting hit. So we don't need to rebuild the world for a quantum internet. The infrastructure is ready. We just need to change the modem. So what good will this do us in our daily lives? You might say, I can already watch Netflix and YouTube videos without any freezing. I can surf the internet at the speed of light. But the quantum internet isn't about speed, my friends. It's about security. Today, every transaction you make on the internet, every password you send, can theoretically be broken one day. But quantum encryption is unbreakable, thanks to the laws of physics. In fact, let me give you an even crazier scenario. In the future, we'll send our data to a quantum computer in the cloud. That computer will process the data and teleport the result back to us. But you know what the strangest part is? The owners of that computer, say Google, Amazon, even governments, won't be able to see what we're doing. So maybe that's when true privacy will actually begin. You know how we always have those doubts? Are my WhatsApp messages being tracked by someone? Are the sites I browse stored somewhere? We're completely right to ask those questions. Because every step we take in today's digital world is like walking in the snow. We always leave a footprint behind, and erasing that footprint is nearly impossible. With technology so advanced, it's like our right to be forgotten has been taken away. But when the quantum internet comes online, the rules will change. Because in the quantum world, trying to observe data without permission means you corrupt the data. Most of the technical hurdles have been overcome. A major step has been taken for the first time on the language problem. Plus, a large part of the infrastructure is ready. That global fiber network is already in place. So, in the age of the quantum internet, the light at the end of the tunnel is finally starting to appear. But amidst all these technological triumphs, one question continues to echo in our minds. What if one day we put not just data, but matter, ourselves, into that machine? Remember, what was the universe's rule? No copying. To go there, you have to leave here. Your atoms must dissolve here, and your information must filter through space and reassemble. The person who opens their eyes on the other side will possess all your memories, your pain, your love. But is that person really you? Or just a perfect copy that remembers your memories? Science can't answer that question yet. Maybe teleporting our bodies will take centuries. But that experiment in Stuttgart might be telling us that even if we can't go there physically, in spirit, we're already there. Just imagine, at the moment of the Big Bang, all the matter in the universe, me, you, the screen you're watching me on, those photons in Stuttgart, we were all inside a single point. We were touching, we were entangled. If quantum entanglement means that particles that once touched can feel each other forever, then maybe we never really separated. Maybe this thing we call distance is just an illusion. That longing we feel for our loved ones, that desire to reunite, it could be our atoms trying to remember the bond they had billions of years ago. Teleportation technology might not physically take us to another place for now, but as humanity, it reminds us that we are much closer, much more connected than we think. Maybe the real revolution starts right here.